Look at the final proof of Sylvester's theorem that shows there are at least two ordinary lines. To do this proof, we need to use duality, as well as a projective plane, as well as the Euler-Poincare formula in the projective plane. We'll get to each step in turn. Imagine we start with the set of points shown on the left. By using duality, we'll get a set of lines shown on the right. To prove that there are at least three ordinary lines in the left picture, we'll need to prove that there are at least three ordinary intersections or points in the right picture. An ordinary intersection is where only two lines intersect. Euler-Poincare formula in the projective plane says the following, that the number of vertices minus number of edges plus number of regions equals 1. To understand this formula, we will need to understand the concept of a vertex, the concept of an edge, and the concept of a region. Let's look at each one in turn. A vertex is the intersection of two lines. The first 5 vertices are easy to spot. 1, 2, 3, 4, 5. However, notice that there is also 6th vertex, which is the intersection of the parallel lines. All these 3 parallel lines intersect at a common infinity vertex, which we label it by 6. Also know that the 6 at the left and the 6 at the right are both the same point, because 2 parallel lines intersect only at one infinite vertex. Now let's look at the concept of edges. Edge is a line segment that lies between 2 vertices. Let's look at the first edge here, 1, that lies between the endpoint red and the endpoint yellow. Notice that as this edge continues to the infinity, it appears from the other side and ends at the yellow endpoint. The infinite edge 2 is the same. It starts from the green endpoint and ends at the gray endpoint. The edge 3 is also interesting. It starts from red, ends at black, and it's different from edge number 4, which starts at green and ends at black. Edges 5 and 6 are also interesting. They both start from blue and end at black, but they are not the same vertex, the same edge. To see this, imagine starting from the blue vertex and going to the right. You will end at the vertex at the infinity, which is black, and will conclude the edge 5. The other edge continues from the black, which is the vertex at infinity, and ends at blue. Edges 7 and 8 are also similarly defined, and these 8 edges will be all the infinite edges that we have in this picture. In addition to these 8 infinite edges, we have 6 finite edges in 2 triangles, 1, 2, 3, 1, 2, 3. And that will raise the total number of edges to 14. Now let's look at the regions. The first infinite region shown in this picture continues to infinity in this direction and also appears over here. So this part of the picture and this part of the picture are all considered the same region. Same holds for the region number 2. It goes to infinity in this direction and appears from infinity from this direction. And so this part of the picture and this part of the picture are all part of the same region. Region 3 is similar. Regions 4, 6, 7, 9 are also infinite regions that are bounded by different segments. In addition to these infinite regions, we have also 2 finite regions, 5 and 8. In total, we have 9 regions. If you look at this formula, you will see that 6 minus 14 plus 9 equals 1. So Euler-Poincare formula holds in this picture. This concludes the description of our Euler-Poincare formula, and let's see how we'll use this to prove the existence of 3 ordinary lines in the Sylvester's problem. We can start by writing the number of vertices using the following formula, where V4 represents the number of vertices with degree 4, V6 the number of vertices with degree 6, V8 the number of vertices with degree 8, and so on. Notice that each vertex has an even degree, because vertices appear when the lines intersect, and they can only make even degrees. Also notice that there is no vertex of degree 2, because it does not make sense. The number of regions can also be written as number of regions where there are 3 surrounding edges, number of regions where there are 4 surrounding edges, and the number of regions where there are 5 surrounding edges, and so on. The number of edges can be counted in two different ways. A region with 3 surrounding edges counts 3 edges, a region with 4 surrounding edges counts 4 edges, and so on. Notice that the region with 3 surrounding edges is a triangle, which could also be infinite. For example, in this picture, 1, 2, and 3 edges surround this infinite region, which will make it a triangle. This other infinite region is surrounded by 4 edges, 1, 2, 3, and 4. Observe that these 2 infinite edges were already counted because they're the same as these 2 other ones. At any rate, there are 2 ways to write the number of edges. One using the number of regions, and the other one is using the number of vertices. A vertex of degree 4 counts 4 edges, a vertex of degree 6 counts 6 edges, a vertex of degree 8 counts 8 edges, and so on. And this again counts the number of edges double, because each edge is adjacent to 2 vertices. By having these equalities, we can now look at the Euler-Poincare formula. We can write Euler-Poincare formula in the following way by multiplying by 3 and then rearranging the terms, and finally getting it as 3v minus e plus 3r minus 2e equals 3. Now what is left is just to plug in the values from the above equalities. 3v equals this, 3 times v4 plus 3 times v6 and so on. Minus e equals this, which we use this line, we only divide it by 2. So we'll get minus 2v4, minus 3v6, minus 4v8, and etc. Plus 3r is used from here. Minus 2e, we use this line. So we get to this equality. If you simplify this equality, you will notice that v4 is the only term that is positive on the left side of this equality. All the remaining terms are negative. Since this equality equals 3, it follows that v4 must at least be 3, because otherwise this equality cannot hold. Remember that v4 is the number of vertices of degree 4. A vertex of degree 4 can only happen when 2 lines intersect. And thus this proves that there are at least 3 vertices where exactly 2 lines intersect. In the primal space, that will mean the existence of 3 ordinary lines. And this proof concludes the last proof of the Sylvester's theorem that we'll see here.